Today's topic I titled as this that robust output feedback controller design using quadratic analysis methods. Uh, it's will be on robust control framework, robust control, how we design the robust controllers, particularly when parameters are known or uncertain parameters are known, or uh, in the uh, backdrop of uncertain systems, particularly towards the design of output feedback controller. Mainly, I will discuss the controller design cases for MIMO systems with other restrictions imposed, for example, structural restrictions imposed, uh, then controller feedback restrictions, all these things imposed, then how those can be designed in static output feedback framework. So if I go to the contents, then this will be the outline of the presentation. We'll discuss the uncertain systems initially, then static output feedback problem, and linear matrix inequalities will introduce how to solve, particularly using simple examples, and we'll show how some of the control problems can be framed as linear matrix inequality problem, and the same tool can be used for guaranteeing system performance, for example H infinity and pole placement, and then we'll discuss some of the available design methods and one of our method, the bottom one, and we'll show a design example case for 2 degree of freedom helicopter systems. It will be broadly an overview sort of presentation, not going into much detail, but I will touch upon the basics of the basic of the know-how on how such problems can be solved, and particularly the difficulty in solving these problems. So there could be many more texts, but I will highlight only the portion that are relevant to this presentation. Texts one can go through for more details beyond what I speak. So if you start with uncertain systems, it's well known, and I've seen that no mathematical system can exactly model a physical one, and modeling errors affect the performance of a feedback control system. So the objective often turns out that how in presence of modeling uncertainty or uncertainties in the system model how to control a system. The approaches or some of the approaches, mostly we are acquainted uh, with these approaches. If we list out, then broadly they can be categorized as the robust control, then model predictive control, and adaptive control. So I will discuss this robust control portion, particularly in the face of uncertainties, how that can be controlled and what is the objective of robust control. Rather, won't discuss or won't compare with other two controls or other control mechanisms in robust control uh, that can handle uncertainties. So for robust control, uncertainty is explicitly dealt with. So the uncertainty, we consider that it's known, the parameter variation, if you consider, then the parameter ranges are known, and obviously a portion of effort for robust control goes on how to model the uncertainties compared to other approaches. And the objective will be design a controller such that some level of performance of the control system is guaranteed irrespective of the changes in the plant dynamics within a predefined class, and the stability is guaranteed. Then it aims to achieve robust performance and or stability in the presence of bounded modeling errors. And commonly designed control performances are regional pole placement, H2 and H infinity control or performances. So we have heard of these terminologies. So we'll discuss some of the conditions by which controller can be designed ensuring such performances. I'll go through mostly state space based method. Won't go to the transfer function based or transfer function interpretation for the uncertainties and corresponding performances. We'll deal with the state space models and particularly the MIMO system case when there are multiple input and multiple outputs. So if you consider first the robust stability, what is robust stability? So if we consider a system as x dot t equal to axt, let's say this is an autonomous system, no input, and how we can say that the system is stable or not. So if this system is considered to be uncertain, that this A matrix is uncertain and it belongs to a set, that this A matrix takes values from this set at different instants of time. We say the system is robustly stable if it is asymptotically stable for all A belongs to this set. For all A belongs to this set. So that does mean something that if you consider an element of this A matrix, and if you say the range of that parameter, and if you try to find that the system, whether the system is stable for each and every parameter, then you will get infinite number of points. And that is the difficulty for solving this robust stability problem or handling the uncertainty problem. So if S is a set of stable matrices, then robust stability is ensured as soon as this set that contains the uncertain A, that is a subset of this S that contains the set of stable matrices. Unfortunately, this is a non-convex set. That means computationally not non-tractable, and I won't go into that convex and non-convex discussions here. But we'll mention these things that robust stability from that non-convexity viewpoint. Robust stability is difficult to check numerically, means to get a numerical solution for a given problem, given data set is difficult. And computational cost is an exponential function of the number of system parameters. So more number of system parameters that are uncertain, if that increases, then the computational cost will increase. This is an example of indirect vector control of induction motor. So this is a case of MIMO system. There are multiple inputs and multiple outputs. So if you see the, I'm not going to discuss how that indirect vector control of induction motor works. I'm using this slide to demonstrate how that MIMO control problem is particularly for practical applications or given an applications, then what are the difficulties faced? So if you look at the controllers, the different controllers available or to be designed for this system, then there are three PI controls. So three PI controls has three inputs, 1, 2, and 3 inputs and 3 outputs. So this is a case of MIMO system with 3 inputs and 3 outputs. And mostly available design methods, they deal with one PI controller to be designed at a time. That is the CISO case. So you approximate the system so that only this input and output is considered, then this one is designed. Then either this one or this one is designed. All are in CISO framework. So that gives a difficulty when you approximate the model to a CISO system and then try to implement that design to the overall system all together, then there will be performance deviation. So then problem will be whether we can design the 3 controllers all together or not. Then you have to deal with this with a MIMO control design problem. And state space method is the most favored design methods or system model expressions for which the generalized control design you can develop for MIMO systems. Another difficulty is that
Sir, please unmute yourself. Sandeep sir, please unmute yourself.
okay,
Mhm.
fine. Is this fine?
Yes, sir. It's
Uh,
fine, sir.
Before this, it was fine. Means I was audible.
Yes, sir.
Okay, okay. So another difficulty with this is that the uh, feedback constraint in the sense that we have to deal with the constraint in the sense this PI controller's input is not used for uh, generating this output, this controlled output. So there is a restriction for that from this input to this output, the gain is zero. So that does mean that the feedback control structure is also restricted. That from certain input to certain output, you have to make that control gain equal to zero. So that adds up another perspective that you have to design a structured control feedback. So I'll move on from here. So we'll start with that system representation. So in state space model, we define that X is a state and represent its dynamics as X dot equal to function of X, U and T. U is the control input, X is the state, and output is G of a G function of X, U, T. We often linearize the system dynamics and represent it in linear form that x dot equal to x plus bu and y equal to cx plus du. A, B, C, D are matrices of appropriate dimension corresponding to the system. If you look at the system model, the linear system model, that this is the output or measured output, and we want to construct the feedback control this U so that certain performance for this overall system can be maintained. So first thing comes into mind that we are using this information and trying to construct this U, then the feedback structure or feedback that we'll choose is this one. U equal to Ks into Y. I kept this S as an argument to represent that it could take a static gain or may have a dynamic one. Means this could be a transfer function one. So for static output feedback, you'll choose that K is equal to K. This is a constant gain. And if you look at this feedback structure, then this is the most desirable structure. Or when you uh, first look at a system given a linear model, then if you think of that, this will be the first controller who will try to design for this system. So for that, if you consider this Y, this output, there will be multiple outputs for a MIMO system case and multiple input for this multiple input case. Then this K will take the structure of a matrix depending on the number of inputs and outputs. For example, for a 2 output and 2 input case, this K is a 2 by 2 square matrix. And if you have other situations, then you will find other structures of this K matching the input and output dimensions. And then closed loop system can be described for the static output case as A plus BKC as you apply this K gain here and neglect this D, then this will be A plus BKC, right? This form you have seen in many cases that when you apply a static output feedback, this comes to this form. Then other sort of controllers, not only that static gain, other controllers, for example, the controller has dynamics as well. Such controllers can also be represented in static output feedback form. For example, if you consider a dynamic controller, that the controller has a dynamics, then this XC is the controller state, XC dot equal to AC XC plus BCY. And the input to the plant will be U equal to CCXC plus DCY. And this AC, BC, CC, DC are the controller parameters to be designed. So if you try to design such a controller, then how to design this? And if you think of that, this controller state as you go on defining, then if you consider that XC is having only a single state, then that will be a first order dynamic controller. And you can think of that corresponding to a transfer function, that this will be similar to a compensator structure. Lag or lead compensator that you have seen conventional. Then if you consider higher order, for example, there are two states in this XC, then you will get a second order transfer function and so on. If you try to represent this dynamic controller as a static output feedback one, then we consider this XCT and augment this plant state as well. And then the system dynamics can be represented in the same form, X tilde equal to A tilde plus BKC. So this K tilde, this contains this DC, CC, BC, AC, these parameters that are to be designed. So the basic structure is that again goes back to that static output feedback problem. So if you can solve that static output feedback problem, then whatever be the order of the dynamic feedback controller we choose, correspondingly this K matrix structure will change, and this A tilde, B tilde and C tilde we can modify this one. For this, obviously this G is a transformation matrix, one has to choose, except that one other parameters will be known and this K tilde to be designed. So that boils down to the problem that we have to design a static output feedback problem. Then other problems are that the commonly used control form is that the PID one. And for the PID as well, you can represent this as a static output feedback problem. So for the same plant, if you consider this UT equal to the proportional part, the integral part and the derivative part, and you have to design this K1, K2, K3, and see that in this framework, we are not considering that this output will be a single one and input would be single one. Still this K1, K2, K3 could be matrices, right? Could be matrices. And how to design this in that, again, whether we can place this one as a static output feedback problem or not. So this integral one introduces new state. So we define that P2T equal to integral of this, then augment this new state and this one, then can represent this one in compact form. Except that this K3dyt, as you replace this yt equal to cxt, this one gets combined to this left hand side, and then you can manipulate and can find a general form of this that will be like this. So this again comes into that Ebert, that linear system form. And if you consider that this one is invertible, particularly corresponding to the derivative gain, if we can keep this one as invertible, then UT again you can choose as a static feedback controller with K bar to be designed. And this K bar contains the PID gain control parameters, this K1, K2 and K3. So this maps back to that PID gain parameter. So if you can design this K bar as a static output feedback problem, then you can compute back this K1, K2 and K3, these the gain parameters. So many such problems can be represented as a static output feedback problem. Then the question arises, what are the difficulty with such design, right? So another structure, you will see that this is a full feedback case. Full feedback means in this case, there are two outputs and four outputs and two inputs. For this four output and two input case, the control gain matrix will be a rectangular 1, 2 by 4 matrix. So if you consider that this K matrix is full, all of the elements are means non-zero and you can design, then that will be a full feedback case, often called as the centralized controller. You will see other situations, for example, the induction motor example I put up at the beginning. In that case, you will see that restricted feedback is there. That does mean from one particular output to another particular input, there won't be any connection and you are forcing those elements are equal to zero. So for example, this is the diagonal elements are non-zero that are to be designed. So for this case, we call this one as strictly decentralized. We will have other restricted feedback cases. For example, this is a tri-diagonal feedback that only the neighboring information for a multi-agent system that is here. So you'll find that in that case, the overall system's control gain structure will be restricted and could be a tri-diagonal one. So these are some of the common problems that are faced when an application is given, and how to design that simple in that static output feedback gain so that the first attempt can be made. So I will introduce the tool that can be used for solving such problems. It's that in the linear matrix inequalities framework. So for a linear matrix inequality, if you have decision variables to be find out, that x1 up to xn and f0 to fn, these matrices are known, and x1 to xn, these are variables that has to be found out satisfying this less than 0 criteria, that this matrix, this fx, this matrix is less than 0. Then when inequalities are in such form uh, are called the linear matrix inequalities, because of this x1 and x1 to xn, that are the parameters to be found out. Those are in linear form. If you consider this one is 0, so otherwise it is affine form, but you can it is commonly called as linear matrix inequalities. And many control problems can be represented as linear matrix inequalities. For example, the Lyapunov stability case, given a system x dot equal to ax, then how to say the system is stable or not in Lyapunov sense, it comes as a linear matrix inequality, A transpose x plus x A transpose less than 0. With that, x is greater than 0, and you will try to find a x satisfying these two inequalities, which is itself greater than 0, and this condition is also satisfied for given A. Similarly, stability for discrete time system, if you see, then the condition turns out to be this one, and you have to find a x satisfying these two conditions. So if this x matrix parameter, if you consider that x as elements as x1, x2, x3, and if you expand each and every element of this x, then that can be expanded in this form, that can be represented in this form, with this f0 to fn are the known matrices. So then this problem, obviously the stability problem to check whether a system is stable, that comes as a linear matrix inequality problem. And many other control problems can also be represented as this. So if you consider a simple example, for example, this y and x are the two decision variables we have to find out, satisfying that y remains greater than 0 and y minus x squared that remains also greater than 0. Find a value of x and y satisfying these two constraints. So this one, particularly using Schur complement, can be represented equivalently as this. And if you see this yx x1, if you take the determinant of this y minus x squared, that will be greater than 0. So that is one of the condition for defining definiteness of the matrices, right? So if you represent this one by expanding as you discussed in the previous slide, so it will be this one, that is a constant matrix, y will be here, this is 1 0 0 0, and x will be here and here, so 1 1 0, this must be greater than 0. So this will be in LMI form with that x and y addition variable. So sum of the inequalities that apparently looks like as a nonlinear matrix inequalities, that can also be converted in that particular LMI form. LMI form, obviously not all, not all. And those tools are available, and many such control problems can be represented as so. We'll see how the solvability of such LMIs are. Several packages available, mostly based on MATLAB. LMI control of toolbox of MATLAB, that's also available. Then simple tools or simple commands you can use for specifying and solving LMI problems. These are the three commonly solved problems or commonly framed problems in LMI form. One is that the feasibility problem, linear objective minimization problem, and generalized eigenvalue minimization problem. I will show the first one, how those can be defined and solved. Then once an LMI problem is specified, it can be solved numerically by calling LMI solvers. There are three solvers available. If you can frame your problem in either of these three problems, then you can call the LMI variable and you can LMI solver and can solve the problem numerically. These are the three MATLAB solvers, MATLAB based LMI control toolbox solvers available, corresponding to these three LMI problems. I will demonstrate the first one. First one is that feasibility problem. Feasibility problem is that x equal to, these are the decision variables. X is a vector containing this x1 to xn, and that satisfies a greater than 0 or this inequality problem. This F is a matrix. The LMI solver, corresponding LMI solver is FISP, and this is the FISP command in MATLAB LMI control toolbox. And if you see the MATLAB code that you have to write for this, so consider that these are the two inequalities, and you have to solve for P. Consider the problem of solving P greater than I and A transpose P plus P less than 0. That's stability problem. Input parameters is that A is known, so this A is a 2 by 2 matrix, and this is the two LMIs how we can define in terms of the defining variables and these inequalities, and then finally we call this our solver. First we define that P is an LMI variable. Its structure is its syntax is so. Then we define the two inequalities. First one corresponds to this P greater than I, and the second one corresponds to the this one. Then we accumulate all these LMI LMI terms that we define, and then call the FISP solver for solving this, and get back this P, this P from the solution. So this is the solution look like. So it converged and given a feasible solution. Best value of T is this, and should be negative for feasibility. T value should be negative for feasibility. So this was a feasible solution and the p-value, if you extract out, then this is a p-value from the set of possible p's. Set of possible p's, I said, because this is an inequality, so it may take or it might be feasible for several different p, and it is just given a particular solution corresponding to the whole possible set of p that satisfies this inequality. Then the other problem is that the linear objective minimization problem. So here not only this constraint that fx is greater than 0, but an objective optimization objective is also added. So you can see this is the combination of the decision variable C transpose X with C is a known vector. So as you multiply C transpose X, then this will be combination of the linear combination of the vector elements x1 to xn. And this you can solve using this min X command. And if you look at such a syntax for solving such an linear objective minimization problem, then this is an example. Minimize trace of x subjected to, this is the constraints. This is the constraints. So this one can be represented, even though this x is multiplication is there, you can represent this one in this form. This is an LMI, and correspondingly this a and b and q values are given. A, b and q values are given. So similar to the previous case, you define that LMI variable, define these LMI terms using these syntaxes corresponding to this set less than 0. Then call this min X function for solving this, and finally obtain the solution or get back the actual solution that minimizes this linear objective. So this is the result of that. If you run this, then it obtained a feasible solution of required accuracy, and the objective value is so and so, and the X solution is given as this. So in that way, that solving an LMI problem numerically is easy. Toolboxes are available, and if you can frame a problem as an LMI problem, then it gives a global solution, because this is a convex problem. So if a solution exists or it converges to a solution, then obviously there exists a feasible set, and if it does not, then there does not exist a feasible set. And it is solved using a iterations. So I'm not going into details of the algorithms that are used to solve, but you can see that it is solved using iteration, and finally it converges to a particular minimized value. I'll move on from here, and we'll show formulation of matrix inequality or linear matrix inequalities problems for some of the simple cases, and we'll show some of the solutions for complex cases. So here we introduce that the stability, quadratic stability, will that is the downstream of that Lyapunov stability. For nominal systems case, x dot equal to x, so we consider a Lyapunov function as x transpose px, where p greater than 0 is a positive definite matrix. So when p is greater than 0 for any state value, this vx will remain greater than 0. And if you find the derivative of this v dot, then this will be pa plus a transpose p, as you replace this x dot equal to x in this. Then objective remains, if you can show this bracketed term, this is less than 0, then v dot will be negative. So v is positive, v dot is negative. Then the states will converge gradually, because vx is defined over this x. So as the value of v decreases over time, then obviously this x will decay, given that this p is constant. So that shows how x will approach to its origin or the equilibrium point for linear systems. And if you write this condition, then this will be pa plus a transpose p is less than 0. And the objective will be to find p greater than 0 satisfying the above. And we have seen how to solve this one for a given a using elements. And we algebraically solved this one earlier using that Lyapunov equation. This is the celebrated Lyapunov equation. A transpose P plus P equal to minus Q. So we choose a Q and solve this P, and finally check the solution is positive definite or not, P is greater than 0 or not, and based on that we decide whether the system is stable. But the alternate form of this is this one, that you solve this condition as an LMI and find a solution P greater than 0. The same if we try to extend for the robust analysis case, particularly when the A matrix, if we consider the A matrix is uncertain, then how to represent that problem or how to tackle that problem. So we'll say that a control law is robust if it is valid over the whole range of admissible uncertainties, mostly offline design. That's why it is cheap, or particularly for implementation. And the difficulty is that the uncertainty modeling is difficult. You should have known the parameter variations, or for a particular parameter. If you consider uncertainty, you should measure that this varies within this to this range. So that information should be known. Obviously, there are other cases when this is not known. Still, you can consider a range of that and do trial and error. So the rover stability is difficult to check, as I discussed at the beginning, and this is exponential of the system parameters. So solution could be in that quadratic analysis framework using Lyapunov's direct approach, that we define E and we ensure that V dot is less than 0. V dot is less than 0. So if this is less than 0, then what happens? Then states will come to the equilibrium point because this V will decay and X will decay. Then quadratic stability will ensure that the system is robustly stable, but the converse is not true. Even if a system is robustly stable, by using quadratic analysis method, you cannot say that if the quadratic tool failed, you cannot say that the system is unstable. System is unstable means there are sets for corresponding to the whole robust stable region, uh, or the set of robustly stable systems, out of which some portions you cannot do or you cannot ensure stability by using quadratic analysis. So from that perspective, this is quadratic stability is at that sufficient conditions. Sufficient condition means if quadratic stability is ensured, you can say the system is robustly stable. Now, if you consider the uncertainty models are commonly used uncertainty models, particularly from parameter variations perspective. Let's say that x dot equal to x and a belongs to the set of a, and we know the parameter variation in that a. Then we can represent the model as this is the nominal value, and this captures the uncertain variation that this ft will vary. D and E are constant matrices, and basically this one to trade off or explore the structure of the uncertain parameters involved with this nominal A matrix, and we have normalized this one as this is less than 1. Obviously, if this may not be less than 1, still you can multiply a scalar parameter either with this D and E and scale down that so that this condition will get satisfied. So for this, to determine this, you require that the parameters are known, or parameter ranges are known. The other approach compared to this norm-bounded one, norm-bounded because we are saying that this norm is less than 1. The polytopic one is that this set is the coset of, these are the matrix vertices, so that the any point in this set that can be represented as linear combination of these vertices. With that, this alpha captures the uncertainty that alpha I summation of alpha I is equal to 1 and alpha I greater than 0. So this alpha I captures the uncertainty, but its vertices are known and that number of the vertices that is finite compared to the infinite number of elements in this A. So then corresponding to this polytopic model also you can determine the stability either of that non-bounded and the polytopic model. The trade-off is that you have to ensure stability for all the vertices and here only this parameter. So this one is non-bounded, one is computationally simpler and this one is computationally heavier because of number of vertices involved. On the other hand, this one in general, the polytopic one in general that is less conservative compared to the non-bounded one because the bounds that we consider that often comes out to be conservative. Then if we try to do the quadratic stability for non-bounded case, then for the non-bounded case, the nominal parameter is A and this captures the uncertainty in that matrix A with this condition. For example, we can consider that E equal to -1 plus delta 1 minus 2 plus delta 2, 3 plus delta 3 and 5 plus delta 4 with this ranges of this delta 1, delta 2, delta 3, delta 4 are known. So you can separate out these uncertain elements, separate out A plus delta A and then that uncertain elements can be represented in this form. For this, the representation or for the linear system case, the benefit is that the particular structure of this Lyapunov matrix that is known to us for linear systems that works. So this structure is known X transpose Px with that P is greater than 0. Then as you take the bound for this replacing the in the V dot, then you get a condition like this with some epsilon 1 is greater than 0. So in this, you can see this is for the nominal parameter case PA plus A transpose P, and this includes the D matrix information and E matrix information that are used to exploit the structure of this uncertainty, and FT captures the uncertain variations. That information is not there, and this is a certain matrix inequality having all the elements or all the matrices unknown. You have to find a P satisfying this less than 0. So that makes that if you find a solution and check that if there exists a solution for this, then this uncertain system will be stable. Uncertain system will be stable. The corresponding algebraic Riccati equation counterpart for this matrix inequality form is this is equal to minus q, the right hand side minus q. So we used to solve this one in algebraic Riccati equation form. This is in algebraic Riccati equation form, and since stable solutions are available for AREs for solving ARE, so we could solve using ARE as well. And this one is in LMI form and we can solve this as an LMI. So I'm not comparing more explicitly these two inequalities, but comparing that this comes out to be an LMI. Then if you consider the state feedback stabilization problem, for state feedback stabilization, the objective is that x dot equal to x plus bu and u equal to kx. Then this is a plus bk into x, the closed loop system, and the stability condition will be a plus bk whole transpose into p as you replace this a plus bk in that a. This will be less than 0. This appears to be, you have to find p and k, both p and k, and as you multiply this will be p, b, k, and there will be multiplication of this p and k elements. So as if it appears as an bilinear matrix inequality because multiplication of two elements are involved. So you will get p1 if it is an element of p and k1, that multiplication will get involved. In airy form, we generally assume a particular structure of K in that Hilbert framework minus R inverse B transpose X, and replace this K here and equate this right hand side with minus K, and represent this one again in that airy form and solve for this P and find this K. In that LMI framework, even though this looks like not an linear matrix inequality, but still you can convert this one as a linear matrix inequality. If we take up and expand that form as this, if we multiply and remove the brackets, then this will be so. So if you multiply P inverse to this front side to all the terms and P inverse from the back side to all the terms, then this one will look like this. So then what happens? Then this P inverse, if you define as a new variable X, then this P inverse will be X, this will be X, and there will be this multiplication of P inverse into K transpose and K into P inverse. So this is K into X. So if you define that K into X is a new variable Y, and if you can solve for X, then you can obtain this K from the solution of this X and Y. So this is an linear matrix inequality again, even though the original one as you derived using Lyapunov's method look nonlinear, but we can convert this one as a linear matrix inequality problem and then solve for X and Y, satisfying this less than 0 condition. And when Y and this X is known, that does mean P inverse, then you can find out this K. So many such problems can be represented as an LMI problem, and we can solve and check that numerically. So this is a case for solving the state feedback stabilization problem for polytopic systems. So if you arrive for the polytopic system problem, when this AB belongs to the set of or linear combination of these vertices, then you have to design a K so that this single K again that stabilizes all the uncertain Ks that are taken by this A and B. See that this K is constant even though this A and B will vary, and they will take values from an uncertain set. So that's the robust stabilization, that will robustly stabilize the system using this control gain K. And if you do the same quadratic stabilization, that defining B equal to X transpose Px, then the condition comes as this. This one is called or known as the common Lyapunov function based approach. In that, the Lyapunov function and its that P inverse term, that X, this is common for all the vertices. This I is 1 to K, 1 to K. So as I equal to 1, you will have one inequality, but that involves the X. If I equal to 2, you will have another inequality, but the X remains the same. So that way, for all the I's, you will define all the inequalities, write them, and solve for that single X that's satisfied for all the I cases. And obviously this X and Y there, X and yi that corresponds to the vertices. If you consider this I is wrong, this should be y, not yi, this is y. And then K will be equal to Y into P. So that single K you can design that stabilizes all the uncertain systems in that set. Then if we come for the performance criteria, one of the common performance criteria is that the poles are placed within a specified damping region. So this theta angle is specified. So if this theta angle is specified, then we know that zeta equal to cos theta. Damping ratio zeta equal to cos theta. And if we can place the poles within this theta angle, then for all the poles that minimum damping of zeta is ensured. So when you have several poles, obviously we can map that damping ratio to second order case. When you have several poles and a higher order system, then it's very difficult to do that. So rather than that, if you can say that all the poles are uh, within this damping region, then minimum damping criteria is satisfied. So the whatever be the number of that complex poles, they satisfy this minimum damping, and their combined response will be this damped response of all these combinations. So this is one of the basic performance criteria when you try to design controllers, that minimum damping is satisfied. Other criteria is often given that it satisfies minimum decay rate. So it's uh, not the imaginary axis, but slightly shifted towards left with this alpha value specified that e to the power minus alpha t. That will be the minimum decay rate that defines that how fast the system poles will decay, or how fast the system poles are. If alpha is large, then your poles will decay fast, and if alpha is small, then it will decay slow. So this one can be defined as a convex LMI region, and for that solutions are available that you can solve the controller parameters so that poles are located within this. So this is the reference for this work. This work is infinity design with pole placement constraints and LMI approach. Long back, 96. So people have solved other problems over that time. Then if you look at the LMI criteria for damping region, then this one is the criteria. This sigma is equal to Ax plus By. We are habituated with this term by this time. So this one is that this plus this transpose. Alpha corresponds to that decay rate, and theta corresponds to the damping factor. So the sine theta cos theta, this corresponds to the damping factor. And this is Ax plus By. So this says that you can design a state feedback controller by solving this X and Y and satisfying this matrix inequality for specified alpha and theta. And if you find a feasible solution, then this X and Y will yield a state feedback gain that satisfies this damping and decay rate criteria. Then other performance criteria are that the H infinity state feedback controller. So for H infinity control, it's that from an input or a disturbance input to a desired output, the transfer function's infinity gain is less than gamma. And if you can minimize this gamma and consider that the input is a disturbance and the output is a desired one, then from that particular input to output, the gain will be minimum. The H infinity gain will be minimum. So that is one of the performance criteria often dealt with in robust control framework. But however, the modeling of uncertainties and how those are modeled and to design in H infinity framework, those interpretations and definitions are not discussed in this lecture. But still, for some of the problems or in some cases, we can define it directly from the state space model. For example, the nonlinearity is that we neglect while obtaining a linear model, those we can consider as disturbances. Then there are other cases or other modeling efforts so that these disturbance and the corresponding desired output that can be modeled. For this, the LMI criteria that comes as for state feedback stabilization is like this. And this one is well known as the bounded real lemma and used explicitly for means used across different applications for designing controllers or H infinity controllers by ensuring performances. So this one you can see, this one is not a feasibility problem. This one is linear objective minimization problem, because you try to minimize this gamma, that is other way you try to minimize this gamma square, And this is one of the variable parameter, and you try to minimize using that min-cx functions. Then we come for the static output feedback controller design problem. So given that some of the common or basic problems we can represent as linear matrix inequalities, what happens for the static output feedback control problem? So for this, consider the linear system again and y equal to cx. So as you replace this one, then it was earlier bk, now the c term is introduced. So that output and state feedback, it's the differentiation is that this y will be equal to cx. And it is no more identity for the state feedback case, similar to the state feedback case. And then the objective is that if you expand this term, you have to find a p and k that involves this b and c in between. And you cannot represent this one as an LMI problem. So that's the difficulty. That's the difficulty with static output feedback controller problem, that it gives a bilinear matrix inequality and you cannot easily convert it into an LMI problem. So some of the approaches available, people have developed how to convert this one, how to approximate this one as an LMI. So we'll see some of the approaches. For example, this is an iterative LMI method. Iterative LMI method, and in this, that particular inequality is converted into this form. And this one you can further represent as an LMI, given that this x is known. This x is known, and this p and k are variable. So then this will be an LMI, and this will be an approximated version of this, with that this x is equal to p inverse. So what happens? We want to solve for this p with some initial value of this x, and then iterate over this so that this x and p, they becomes or they converge to each other. So in that, first a solution for p is obtained, and then assign this x first iteration is equal to p. Then iterate over this means once this x is known or an initial value is taken, you solve this one as an LMI, then go on solving and putting back or updating the x value using this p so that it converges to some solution. So step 2 will be for the ith iteration, solve this optimization objective. Then finally, when this x minus pi that is less than delta, this norm will be here, that is less than delta, then you will say that it has converged. Some pre-specified value of error. So that is one of the iterative method for solving the static output feedback problem. Other ways are that you directly or approximate that bilinear matrix inequality as best as possible and represent this one as an LMI itself rather than iterating over that x and p. So this will be a general representation of that H infinity control problem, that x dot t equal to axt plus bwwt plus but. So this is the control input. This is the control input. This one will treat as the disturbance input to the system. This is the measured output, means this ut will be used to construct this control input, and this is the desired output. Desired output in the sense we'll try to minimize the infinity norm corresponding to this input to this output. In cases you can consider that yt equal to zt if it is not appropriately defined. Then if you take a static output feedback for this, then the closed loop system for w to z will look like this with the parameters you can define this way. Then we'll try to minimize the infinity norm for this, and that you do using the BRL lemma, that bounded real lemma, And this is the result corresponding to the bounded real lemma that the infinity norm of this TZW is less than gamma, and the closed loop system matrix is Hurwitz means stable if there exists this p greater than 0 satisfying this inequality. So this ACL that contains that VKC term, and when it is multiplied with this P, then this is a bilinear matrix inequality, and that is difficult to solve. An alternate form of this is this one, that if you multiply P inverse pre and post multiplied, then you will get that X is post multiplied to this ACL compared to P multiplied to this ACL. Then since BKC is involved, so what we do, we approximate this one using that range space and null space of the C matrix, null space and range space. So that Lyapunov matrix X is decomposed using that uh, QC and RC, these two matrices. And if you write that y equal to KCX, this term, then this comes as that YC into RC transpose plus this nonlinear term. Then YC into RC transpose is basically that this gives that K back to us with this change of variable, but you have to take care of these nonlinear terms. So we take care by further manipulation and obtain an LMI corresponding to this, and it will look like this condition or static output feedback control problem. So if you find a solution for this less than 0 with appropriately defined system matrices and the variables here, and then this TJWS will be less than gamma. So that is one of the approach that we obtain sufficient condition corresponding to those bilinear matrix inequality for static output feedback problem. The benefit is that if you find a solution for this, then many of the control problems you can solve using this algorithm. And obviously, since approximations are involved, as I shown, these conditions are sufficient, and conservative may not keep the exact lowest conditions. So there are always hope for improvement for such designs. So then you design a controller K equal to this. And in this LMI framework, compared to as we did for ARD or algebraic Riccati equation, is this the structured form of K you can design. For example, a structure of K, if you consider that this is equal to K11, K12, and these particular elements are not there, they equal to 0, then you can consider the variables, this XR to be a diagonal one, and this YC takes the structure of this K. And if you solve this one and that LMI, then you will get back the control gain in this particular form. Then you can apply to your system. So not only that H infinity control problem, but also the pole placement in conic sector. For that also you can approximate and obtain solution, LMI based solution for this. And I'm not going to explain, just to give an impression of how that inequality would look like. So if you want to solve, then you have to go on defining the variables and then look at the terms, expanding the terms, and then finally have to solve this. So then you can solve that performance criteria as well. As you take up an example, then we can see that this is a fifth order system. Its B, BW are given, C is given, and our objective is to design a static output feedback controller. So we designed this with the pole placement criteria that theta equal to 60 degrees. So cos theta gives the damping factor corresponding to this, and we consider different structures of K. So as you can see, this is the full centralized structure. This is that tridiagonal structure, and this is fully diagonal structure. And as you go on restricting the feedback paths or feedback loops, then obviously your performance will deteriorate. So you can see, look at the solution. So we have optimized that H infinity gain and obtained the optimal value. So when you have full freedom, then the disturbance to the desired output, the gain is less, right? Then as you put more structural conditions, restrictions on this, then you will get slightly higher gain value. And then as you put more restrictions, then you will get more higher value, further higher values. So that shows two things. One is that the control problem using the two main design performance criteria, that H infinity and pole placement, that could be solved using this. And then the different structures of the key that can be exploited, means we can design the key using different structures or restrictions. Then I will take up an example for a laboratory scale helicopter system. So this is a Quansar make laboratory scale setup for a 2 degree of freedom helicopter system. So the objective is that you have to keep this helicopter model fixed at particular two angles in two planes. So the model can be described as this. Uh, so the states are x1, x2, x3, x4. These are the pitch angle, the EO angle, and the two planes corresponding to the 2 degrees of freedom and the corresponding velocities. So these are the 4 states. And if you see this one, then this is a nonlinear model. This is a nonlinear model. So nonlinear model, how we have handled. Well, linear is this one around an operating point, and then design the controller corresponding to that. Then its limitation is that as you approximate using that Jacobian or Taylor series approximation, then you are neglecting some modeling errors. So the controller that you design, that may not perform well corresponding to the actual system or actual model. So what we try to do for this system is that we considered these nonlinear terms as uncertain parameters, and try to represent this one as a polytopic model, and design the control input for this. So what is, if you see the control inputs, then there are two control inputs. We have two rotors, one in this direction and another rotor in this direction. So two rotors. So we have two inputs corresponding to the two rotors, and this is a MIMO system. So you can consider that both the angles are measurable. So if you take only both the angles, then this will be a output feedback problem. If you consider along with the angle, if you find the derivative of this, then velocity can be determined. You can consider the this as a state feedback problem. But in both the cases, there will be two inputs you have to design. So these are the parameters of that 2D of helicopter model. I'm skipping this one. And the objective that we defined is that x1 is uncertain but bounded, considering that x1 is the particular state lies within a range. Then if we define this one as an uncertain parameter, then we can find a bound for this parameter. Then this model will be a linear uncertain model, and we can design a robust controller for this. So the assumption is that we are considering the variation of the pitch angle that it remains within a particular range. So that is a particular modeling consideration in the direction of that robust control, that you have to model it as best as possible. So if you consider a larger range of this pitch angle, then your uncertainty range will increase, and the control will be applicable for larger range of that pitch angle. So then as you define this one as an uncertain parameter, then the model will be like this, that this A will be a function of rho plus this can be defined appropriately as you define. We have defined this way, that BW is this, and CZ equal to all these states, and we will try to minimize the effect of this W1 particularly entering into this channel to all these states. And this is a row matrix, so this depends on this row parameter, this uncertain parameter, except this one, this model becomes linear. So when you take the range of this row, then you can represent this one in either that non-bounded parameter form, non-bounded uncertainty form, or in the polytopic form. So we took up the polytopic representation. So we took new one and new two. Since this is a single row element or single uncertain parameter, we will have two vertices. So we will have that A1 and A2 two vertices. So that we obtain. So once we obtain this one, then the control problem, we can see that this is your twin rotor memo system or that helicopter. It has four outputs, and mostly that PI feedback is used because you want to make that error equal to 0. So when you go for using that PI feedback, so I don't know how many of you tried to use a integral feedback, particularly with the state feedback controller, and when particularly angular references are given, that you maintain the pitch and EO angle as so and so. So if you look at this structure, then this structure, and particularly compare the output or the position with the reference position or the angular positions, and then generate the error and try to design a PI controller corresponding to this, then you can see that this input is not interacting with this controller, and this input is not interacting with this controller. So this is in structured form. So if you try to implement the controller in this particular structure, rather than the centralized one, you have to design the controller in this particular structure. So we take up different such structures and define the control problem, and design this. So we took up that this PI form KPXT plus multiplication of this YT we defined as the two position. This is the first position, this is the second position, pitch and EO equal to C into XT. Then define this one in that static output feedback framework, similar to that we discussed at the beginning. Then this one will be K equal to Kp into Ki, and from this X tilde T, you will feedback or will generate the control input K. And the control objective will be to satisfy equivalent problem for that H infinity control problem for polytopic systems, that you minimize the L2 gain criteria and the regional pole placement criteria, and design a static feedback controller, static output feedback controller. So the criteria for polytopic systems would look like this for state feedback case. And since this is a very delicate system, you cannot use very high control gain, then your actuators or rotor inputs will get saturated and you won't get the control effects. So we limited the gains by using these two conditions, and finally minimized, subjected to that control LMIs, and finally we considered the theta equal to 20 degree and gamma equal to this one, and solve this problem. These are the numerical values of that A1, A2. So you can see, okay, this should be, This is minus 0.3905 and this is 0.3905, and this is here plus and this is minus. So these are the two vertices and the uncertain model that lies within these two vertices or linear combination of these two. Then this is variation of the pitch angle. Pitch angle we compared with other existing controllers, and this one we designed that robust PI centralized one. Centralized means it takes all the inputs and generate all the outputs, and the control feedback is not particularly structured. So, and optimal LQR and LQR. So in all the cases, it works as you design using this. And this is the response of the EO angle. And this is a comparison for the centralized and decentralized case. So that does mean that as you consider the decentralized or diagonal control design, not the centralized one, then this red one is the decentralized one and green one is the centralized one. So you can see that response is almost similar for the pitch angle case, with the centralized one giving slightly higher oscillation that could be because of the coupling of the two plane dynamics. So if one is oscillating against the other, and for the decentralized case, basically that coupling is not there through the control feedback. So in that case, you might get lesser oscillations, but it's not necessarily that it is due to that particular structure. And then variation of control input are this. So this is for the pitch angle, and time variation of the control input for the EO angle. The left hand side one, the centralized case, right hand side one is the decentralized case. So in both the cases, this is around 12.5, this is 12, and here around 0, this is also around 0. So this is almost in the similar range for the control input. And if you compare the performances using the commonly used performance criteria, that integral, absolute error, and square error, then this one gives slightly better performance because of that lesser oscillation. Uh, but it's not the might not be due to that structured form that we considered. Then comparison of controller gains. If you see that the centralized case, it uses the full control gain, whereas for this case, we have structured control gains. Means we don't feedback from one output to another input. Only that pitch angle control input is generated through the pitch angle output. Similarly, the other one. Then as I have shown that you have to keep the control gain minimum. So what it would be if you consider the saturation constraint as well, rather than doing the control gain or reducing the control gain arbitrarily. So that also can be represented as an LMI problem and can be solved in this framework. So we solved that problem as well. And this is the LMI condition corresponding to this. And we have again PI controller, output feedback PI controller, this one. But the centralized one, control gain equal to KP and KI. KP and KI for the two cases. So we have four gains corresponding to the four outputs and two inputs. So four outputs at the two positions and the two integrals of the positions, and outputs or control inputs at the uh, input plots. So that output feedback case as well means the tracking corresponding to the pitch angle reference change that happens, and for the EO angle as well. And it performs well even though we considered the actuator saturation and included that performance in the design. And this is again the experimental result for the variation of the control input for the output feedback case. So initially there are oscillations. Then once it settles down, then due to the change in the reference angle, uh, it is tracking well compared to the initial control input is very large because it gets deviated from the reference demand largely initially. But later, when you change the reference demand slowly or using small variations, then your control input will be smaller. But still, it remains within the saturation region, or it does not saturate it, since the design is based on considering the saturation condition. So these are some of the references. First one is the classical book on linear matrix inequalities. There are other books. This is one of our recent publication on that static output feedback control design, particularly in the age infinity control and regional pole placement. So that can be applied to so many applications. And others are classical books and some of the references from output feedback. So I'm finishing here. Uh, Thank you for listening.
Thank you very much, sir.
So I hope I have finished on time, right?
Yes, sir, exactly on time. And now we may enter into the question answer session. So
Yes.
participants, please.
So if you want me to elaborate any portion, or if you could not understand a certain step, obviously you can raise, I can repeat, no problem at all in that. But I have given an overview of how these problems can be solved. So even you can write your questions in the chat box.
Yes, sir. That's for what we are waiting. Really, they used to write. Still, I can see there is no question, but I think they will be writing soon.
Okay.
Participants, please, if you have a question, so you can write in the chat box, or even you can unmute yourself. And since there is no question on the screen.
Hello. Good evening,
Yes.
sir.
Good evening. Good evening.
Sir, you made some linearizations over there for non-linear model.
Yes, exactly.
Okay, for 2 degree of freedom helicopter applications.
Yes.
So,
Yes.
for which parameter you are concentrating more over there, sir?
So I'm not able to see who is speaking.
So I'm Ravi Shankar Desai from BITS Pilani, Goa, sir.
Okay, okay, okay,
Yes,
fine, excellent. So thank you for your question. So I'll go back to that application slides. So it is slightly tricky, and we published few papers in this line, particularly considering the model with the nonlinear parameter as an uncertain one. Okay, so if you look at this model, then here this x4 cos x1 into sin x1. If you consider this x4 cos x1 into sin x1 as a parameter, then this one will be my d2 square into some parameter into x4. So that's a linear one, right? So if you consider that way, that x4 cos x1 into sin x1, that is an uncertain parameter, considering the bound for this x1 and x4, that this will operate within this range, then this rho will be an uncertain parameter and will appear in that particular model. And the remaining portion then will be linear. Remaining portion will be linear. So the same thing we applied for the input or other nonlinear terms. For example, if you consider this term as well. So this will be again that rho parameter that we defined here. And when you consider this as a rho parameter, considering the range of this x4 and x1, then this element will consider that this is uncertain. And this will get multiplied with this, and this whole term or the element in that matrix will be uncertain. And this x3 will remain, and that will correspond to a linear element. Right? Are you following? Then
Yes.
Then we have not linearized the model around an equilibrium point at all. So we did obtain the linear model by approximating those nonlinear parameters or defining them as an uncertain parameter and taking the range of that. So that modeling portion is tricky for robust control cases. And then once that is defined, we define a polytopic model. Obviously, that is an approximation when you consider the ranges of x1 and x4. And further, you can do improvement in the control performance by using LPV controllers and other controllers if you know that particular rho parameter. So that scope is there.
Okay. Thank you, sir. Thank you. Thank you, sir.
Okay. Is that clear?
Yes, sir. Yes, sir. Yes.
Okay. Thank you. Okay, I can see few other questions that Mr. Sushant.
Sir,
Yes.
actually I was muted. I read. You got the question, sir? Can you see the question?
Yes.
Okay, sir. Okay.
So, how can a robust PID controller be designed for systems with parametric uncertainty? Or parameter uncertainties, right? So, Susan, obviously that problem is difficult, and maybe the solution is not available in textbook. So that's what was my objective, that give you the clues so that you can solve. You can try it yourself. So this one is the initial slide that I shown, that PID controller as SOF control design problem. So if you consider this x dot t equal to xt plus BUT, then ut equal to the PID gains K1, K2, K3. In the model, you can represent as a static output feedback problem, right? And then if you consider that this A bar or the actual plant matrix is uncertain, then you use any static output feedback control problem. The solutions for this static output feedback framework. Obviously, that you have to link. For example, this paper particularly takes the H infinity controller design with the regional pole placement. So that does not take care of uncertainties explicitly in the sense that the polytopic formation or non-bounded formation. But you will find other papers that considers the particular parametric uncertainties and solve the problem using that. But obviously, the method, if you follow in this paper, that can also be extended for that parametric uncertainty cases, or when there are uncertain parameters present. Means using the method, you can go back to that defining Lyapunov function, and if you follow that design method, then you can develop your own method for non-bounded uncertainties and or other polytopic system cases. And there could be few more papers in this direction from us in that static output feedback in the polytopic framework or similar framework. Is that okay, Susan? Susan, could I answer your question?
Yeah, yes, sir.
Yes, sir, I got the points. Thank you, sir.
Okay. Excellent.
Sir, there is another question by
Yes.
Divya Pandey.
What are the uncertain Okay, please, you read. Yes. So Dibba written that what are the uncertain parameters which affect the model based with time delay system? So Dibba, it's a very open question that you have asked. If it is not particularly some application example and it is not known to me, it is difficult. In general, time delay system, I don't know which time delay system you are talking about. So if you consider linear time delay system, that we in general represent as x dot t equal to xt, x dot t equal to x plus at minus tau, right? So that A or AD matrix that they may means take up uncertain values based on how you are representing your system or how good your model is or how good you are in deriving your system model. For example, if you take up a simple DC motor control problem that you have studied, all of us have studied DC motor control problem using remote controls. Right? Remote means you're controlling somewhere else. You are sitting in your lab controlling a DC motor that is located somewhere else or in some other lab. You are transforming the data or input and control data through the network that are available through you. Then you will get a delay in the feedback loop or control loop. And if you try to represent the system model, then it will take the parameters of the DC motor. Now, DC motor parameter itself is subjected to variation. For example, if you consider the armature resistance of the DC motor. So as the motor runs from the initial starting position, then it will get heated up and it will change. So if you still want to guarantee performance corresponding to these variations or accounting for these variations, then you have to model that RA for that DC motor that you have considered and have to take certain ranges based on or either estimating or measuring or considering a model for the variation of the resistance, and that you have to represent in the DC motor model that finally come into your delayed system so that A and AD that comes out from the actual application that will have that parametric variations. If you would have included these variations properly or appropriately. Is that okay, Dibba?
Divya Pandey, please respond.
Yes, sir.
Is there any other specific doubt with this? Means, are
Yes,
you
sir.
talking about any specific doubt?
Yes, sir. If I use the ID control.
Okay, excellent. Then, okay.
Yes, sir.
I got another question. Can I? Yes. Kamaraju Vechalaru. So if I pronounce it correctly, can I use pole placement technique to an spectral system? Pole placement is a classical problem, right? So pole placement is done with obviously many objectives. So as you choose the poles that satisfies many criteria. For example, the transient response criteria. Transient response criteria that it will have certain damping factor, then decay rate, and all this. And improving stability, obviously, when you talk about that, how fast the system will respond, or how fast or how much the variations it can take up till the poles comes or moves from left hand side to right hand side, or the poles become unstable. So obviously it takes care of the stability, or that in other way you can say the variation towards that robustness, that as you vary the system parameter, then still the system will remain stable. Is that fine? So thank you. Thank you. Thank you.
So I think, sir, the question answer session is also over now.
Okay. Thank you.
Okay.
Thank you for listening.
Thank you very much, sir, once again. So accepting our invitation so promptly and delivering such a nice and wonderful lecture. I hope all the participants have been benefited through this. This will open their thinking, and this might help in their research. There are few research scholars as well, so they might use these directions to their research work.
Okay,
So,
I will be
thank
very
you.
happy, and will be happy to help if you have any doubt. Happy